Researchers have found evidence of a cataclysmic energy flare that began near the supermassive black hole in the center of our galaxy. This catastrophic flare punched through both poles of the Milky Way far into deep space, creating two enormous ionization cones. The discovery can lead to a complete reinterpretation of our galaxy's evolution. The flare, officially known as the Seyfert flare, was so powerful that its impact was felt 200,000 light-years away, smashing into the Magellanic Stream, a long trail of gas extending from the nearby Large and Small Magellanic Clouds, dwarf galaxies orbiting our Milky Way. A team of researchers from Australia and the United States says the explosion was too huge to have been triggered by anything other than the nuclear activity associated with the supermassive black hole Sagittarius A, which is about 4.2 million times more massive than the Sun. Using data gathered by the Hubble Space Telescope, the researchers calculated that the massive explosion took place little more than 3 million years ago. During that time on Earth, the asteroid that triggered the extinction of the dinosaurs was already 63 million years in the past, and humanity's ancient ancestors, the Australopiths, were roaming in Africa. The researchers estimate the blast lasted for about 300,000 years. Using a new method for hunting nearby black holes, astronomers spotted a huge stellar black hole in our galaxy bigger than ever thought possible. This method will help us find many more black holes in the near future. Stellar black holes come from the death of stars, and despite billions of stars that exist in the Milky Way, we have only discovered a handful of these black holes. Until now, scientists had estimated the mass of an individual stellar black hole in our galaxy at no more than 20 times that of the Sun. But the latest discovery changes everything. The newfound stellar mass black hole is 70 times the mass of the Sun. It lies 15,000 light-years from Earth, and researchers call it LB1. The Milky Way galaxy may contain about 100 million stellar black holes. Until recently, stellar black holes could only be spotted when they were seen eating up gas from a nearby star. This process creates powerful X-ray emissions detectable from Earth that reveal the presence of the collapsed object. The problem here is that most of the stellar black holes in our galaxy aren't eating stars, therefore we cannot detect them this way. But that's when Professor Jangle of the National Astronomical Observatory of China, together with collaborators, observed the sky with China's Large Sky Area Multi-Object Fiber Spectroscopic Telescope, looking for stars that appeared to be getting pulled towards the gravity of an invisible object. After using that technique, follow-up observations using the powerful Gran Telescopia Canarias in Spain and the CAC Observatory in the US, revealed a star 8 times heavier than our own Sun orbiting the massive black hole every 79 days now. Scientists will have to re-examine their models of how stellar mass black holes form. A team of astronomers spotted a runaway star called S5HVEs 1 traveling through the Milky Way at roughly 3.7 million miles per hour. The gravitational forces of Sagittarius, a supermassive black hole, caused the star to travel at such high speeds. The star lies in the constellation of Gru, and travels 10 times faster than most stars in our galaxy. The high-velocity star will inevitably leave the Milky Way and never, return. What makes S5HVEs 1 so interesting is its high speed and close passage to the Earth, only 29,000 light-years away, which is practically next door. By astronomical standards, we never knew about these ultra-fast stars until about 2 decades ago. They travel at sufficient speeds to escape the galaxy by overcoming its strong gravitational pull. It takes an incredibly massive object like the 4 million solar masses Sagittarius A to accelerate these stars at such velocities. Scientists think the black hole ejected the star with a speed of thousands of km/second about 5 million years ago, a time when our ancestors were just learning to walk on 2 feet. Originally, S5HBS 1 was part of a binary system that got too close to Sagittarius. Therefore, the supermassive black hole swallowed one of the stars and ejected the other at high velocities. This process is called the Hills mechanism. The runaway star was discovered using the 3.9M Anglo-Australian telescope with the help of the European Space Agency's Gaia satellite. The researchers also discovered the full speed of the star and traced its journey right back to the center of the Milky Way. For decades, scientists have theorized that there is a 9th planet orbiting our Sun. Based on their suggestions, the planet could be 10 times bigger than Earth and 20 times further out from the Sun than Neptune. The scientists who predicted the planet's existence did So based on the strange, highly elliptical orbits of around 30 so-called trans-Neptunian objects, another weird feature is that the Kuiper belt, a circumstellar disk full of icy asteroids, comets, and dwarf planets which encompasses the solar system or orbits in the opposite direction to the planets within it. But recently researchers published a paper on Archive titled, "What if Planet 9 is a primordial black hole?" It suggests that the ninth planet is actually an ancient primordial black hole about the size of a tennis ball. Primordial black holes have formed soon after the Big Bang, 13.8 billion years ago. Astronomers believe primordial black holes with the lowest mass have probably evaporated, however the larger ones may still exist, even though we have never directly observed them. Because primordial black holes formed so early on in the existence of the universe, they are much smaller than their modern counterparts. However, now it could be a very difficult test for scientists to confirm this theory. With a mass of around 5 Earths and a radius of about 5 centimeters, the hypothetical primordial black hole would have a Hawking temperature of approximately 0.4 Kelvin, making it colder than the cosmic microwave background. Thus, the power radiated by a typical primordial black hole alone is very small, which makes it pretty hard to detect. If the hypothetical Planet 9 did turn out to be a black hole, it would also explain why it has been so far impossible to detect, as researchers have so far been looking for an object in visible light. But the researchers now propose examining cosmic rays and gamma rays which could be emanating from the small black hole. Supermassive black holes can have major impacts on the evolution of a galaxy, especially when they drive powerful winds. When a black hole consumes its galaxy's material, the galaxy becomes an active galactic nucleus. During this phase, the black hole is growing in mass and gas is being driven out by energy from the active nucleus. For this research, astronomers used the AMIR infrared spectrograph on the Gran Telescopio Canarias to study ionized and molecular winds. The researchers found the ionized wind is faster than the molecular wind, reaching up to 1,200 kilometers per second. The molecular wind is emptying the galaxy's gas reservoirs at up to 176 solar masses per year, seemingly preventing new star formation. Now astronomers want to observe a complete sample of obscured nearby quasars to study their ionized and molecular winds. This will allow scientists to directly confirm this effect on the evolution of galaxies. First of all, we don't know exactly when the first black holes formed, but there are theories in the present-day universe. Black holes are formed when massive stars run out of fuel and collapse in on themselves. So a theory is that perhaps there were no black holes until the first giant stars collapsed, igniting a cataclysmic supernova explosion, and leaving behind a black hole perhaps 400 million years after the Big Bang. According to this model, the first black holes acted as nuclei for the creation of galaxies, drawing in raw star-forming material from the universe around them and growing in size to become the supermassive black holes with a mass of millions of suns that lie at the core of many of today's galaxies. In 2011, NASA's Chandra X-ray Observatory confirmed the presence of growing black holes in the heart of many distant ancient galaxies, which strengthens this theory. But another theory is that the first black holes were born in the first second after the Big Bang some 13.8 billion years ago, so supporters of this idea suggest that in the first moments of creation, pressures and temperatures were so great that slight fluctuations in the density of matter could create black holes spontaneously, which could then have acted as the seeds for later star and galaxy formation. Black holes are extremely hard to detect simply because they do not reflect light. The gravitational whirlwind of these black beasts pulls inward with so much force that even light can't escape their grasps. Even though we cannot see a black hole directly, we can detect the surrounding matter funneled by its gravity into a disk around it. As matter falls in, it settles in a disk around the black hole that can get very hot. Some of the energy released from falling in is turned into light, which we can then see in X-rays, which can be detected by X-ray telescopes, such as the orbiting Chandra X-ray Observatory. Another technique used for detecting black holes is looking at how objects near one behave. For example, at the center of the Milky Way, we can see an empty spot where all of the stars are whirling around as if they were orbiting a really dense mass. That's where the black hole is. We can detect the motion of these stars with different ground-based telescopes like the Very Large Telescope and with space-based telescopes such as the Hubble Space Telescope. When galaxies collide, it means the supermassive black holes at the center of each galaxy collide as well. Recently, astronomers have detected a triple collision of galaxies, each containing a supermassive black hole. For this discovery, astronomers needed to combine data from telescopes both on the ground and in space. Several observatories like the Chandra X-ray Observatory and other NASA space telescopes have witnessed this unusual event, which is located 1 billion light-years from Earth. First, the Sloan Digital Sky Survey Telescope in New Mexico imaged the system in optical light. Then citizen scientists involved in the Galaxy Zoo project helped tag the system as a galactic collision. Shortly after, NASA's Wide Field Infrared Survey Explorer revealed glowing infrared light coming from the collision. To follow up on these clues, astronomers then turned to Chandra, which revealed X-ray sources at the bright centers of each galaxy just where the supermassive black holes are expected to reside. Finally, NASA's Nuclear Spectroscopic Telescope Array spotted gas and dust around one of the black holes, typical for an emerging black hole system. When researchers combined all this data, the final result revealed active feeding supermassive black holes. While astronomers have observed pairs of black holes before, this is the first time they have witnessed a trio. Finding a triplet of supermassive black holes is very difficult because the gas and dust created by the galactic merger can hide the event from our view. But this is all thanks to our powerful telescopes, which can see in different wavelengths rather than optical light. Eventually, the trio will merge into a larger one, producing gravitational waves or ripples in spacetime, which can be detected here on Earth by radio telescopes for the first time ever. An international research team has observed 3 supermassive black holes at the core of the galaxy, NGC 6240. Every galaxy, including our own Milky Way, has at least one massive black hole that powers them. But scientists have now proved for the first time ever that a galaxy can have not one but 3 supermassive black holes. NGC 6240 is known as an irregular galaxy. Due to its unusual shape, the galaxy lies around 300 million light-years away from us, which is pretty close by cosmic standards, and due to its proximity, astronomers have been able to study it in all wavelengths of light. Previously, astronomers thought the collision of 2 smaller galaxies created NGC 6240, and therefore thought the galaxy contains 2 black holes in its core, until they found the third one. Each of them has a mass of more than 90 million suns. The researchers obtained the new observations of the galaxy, using the European Southern Observatory's Very Large Telescope in Chile. These galactic ancestors move towards each other at velocities of several hundred km a second, and they are still in the process of merging. All 3 of the black holes lie in a region of space less than 3,000 Lutar. Across this discovery will help us understand the evolution of galaxies over time, especially the largest galaxies in the universe. Black holes are incredibly fascinating, invisible beasts lurking in space, sometimes ripping passing stars apart and scattering their remains. But how do they form? First of all, they are definitely not holes. Rather, they're a great amount of matter packed into a very small area. Imagine a star 10 times the mass of the Sun squeezed into a sphere roughly the diameter of New York City. Its gravity becomes enormously strong. However, different types of black holes form through different processes. Stellar mass black holes are born when very massive stars, tens of solar masses, can no longer produce energy in their cores and explode as supernovae. After the outer layers are violently ejected into space, the remaining core collapses under its own weight to form a black hole. As for the formation mechanism of supermassive black holes, there is still debate. It is generally agreed that a black hole at a galaxy's center can become supermassive by accreting matter and merging with other black holes, but the origin of the progenitor black hole remains unclear. Astronomers have spotted strange flashes coming from the Milky Way's central black hole, Sagittarius A. In May, observers using the CEC telescope on Mauna Kea saw unusual blasts of radiation, an infrared flash that became about 75 times brighter over the course of just 2 hours. The researchers suggest the flashes could indicate that our central black hole has become more active, or that it has started accreting more or different material. Once the black hole starts eating nearby objects like stars or dust clouds, the infalling material heats up at the event horizon, lighting up the region even though the gravitational field there warps space so that light can't escape. Telescopes can still pick up the radiation coming out of the event horizon. Astronomers speculate that the flash was thrown out when a star known as S2 moved close to the black hole in 2018, disturbing gases at the event horizon enough to cause the flashing event. Another reason might be a cloud of dust known as G2, which passed about 36 light-hours from Sagittarius A in 2014. However, more observations might shed light on this mystery. Black holes usually tend to destroy stars, but researchers have just witnessed a black hole that is actually helping to nurture and spark the birth of baby stars across multiple galaxies. Yep, the black hole is impacting stars in more than 1 million light-years from its origin. For this, astronomers use NASA's Chandra X-ray Observatory and some other telescopes. The supermassive black hole lies at the center of a galaxy 9.9 billion light-years away from us, and there are at least 7 galactic neighbors around there. Black holes devour everything caught within their gravitational pull, but they can also release highly energized jets of material that spew particles at the speed of light. Previously, scientists detected radio wave emission from a jet of high-energy particles stretched for 1 million light-years. Follow-up observations from Chandra revealed the black hole to be the source of the jet. Chandra can detect the extra X-rays created by hot gas that swirls around black holes. The Space Observatory also detected a diffused cloud of X-ray emission surrounding one end of the radio jet. Scientists think this emission is most likely coming from a gigantic bubble of hot gas heated by particles in the jet when they interacted with the surrounding matter, so the researchers determined that the gigantic gas bubble expanded and actually moved across 4 of the neighboring galaxies, and that may have created a shock wave that compressed cool gas in the galaxies, causing stars to form. All 4 galaxies are about 400,000 light-years from the center of the bubble. The researchers believe star formation in these galaxies is 2 to 5 times higher than other similar galaxies. Months ago, astrophysicists at Western University have found evidence that shows black holes don't necessarily need to emerge from a star remnant. This may explain the presence of extremely massive black holes at a very early stage in our universe. Shantanu Basu and Arpan Das from Western's Department of Physics and Astronomy have developed a new mathematical model explaining the observed distribution of supermassive black hole masses and luminosities. Researchers suggest that supermassive black holes actually form very rapidly over a very short period of time and then suddenly stop growing. The new model calculates the mass function of supermassive black holes growing rapidly in a short space of time. This explanation contrasts with the current understanding that stellar mass black holes form from collapsing massive stars. Until now, theories suggested these black holes emerge from stellar remnants, but the new evidence suggests black holes originate from direct collapses, not stellar remnants. During the last decade, astronomers have observed many of these objects at high redshifts dated to within 800 million years after the Big Bang. The idea of these ancient black holes challenges the current understanding of how black holes form and grow. Basu believes they can combine these results with future observations to inform the formation history of the extremely massive black holes that exist at very early times in our universe. New research shows scientists might have been missing an entire class of black holes that they didn't know existed. In a study published in Science, astronomers offer a new way to search for black holes, suggesting a class smaller than the smallest known black holes. Black holes are the corpses of what used to be massive stars that explode and ultimately collapse in on themselves. But not all stars turn into black holes. When some stars die and collapse, they form neutron stars, which are small and incredibly dense. The search for black holes and neutron stars helps researchers piece together how the universe works and how stars live and die. If astronomers only focus on supermassive black holes and neutron stars, they can miss whole demographics. Researchers analyzed data from the Apache Point Observatory Galactic Evolution Experiment, which collected light from 100,000 stars in the Milky Way, then spotted a giant red star that seemed to be orbiting something. Shifts in the star's wavelengths could show it was orbiting an unseen companion. Based on their calculations, it had to be smaller than any observable black holes found in the Milky Way, but way bigger than most known neutron stars. After further calculations and additional data from ground telescopes and the Gaia satellite, they realized they had found a low-mass black hole likely about 3.3 times the mass of the Sun. Most galaxies have a supermassive black hole at their center. A few, though, contain not one but 2 black holes. This is NGC 7674. The brightest and largest member of the Hickson 96 compact group of galaxies. The galaxy lies in the constellation Pegasus, about 400 million light-years away from Earth. The center of this spiral galaxy boasts a pair of black holes orbiting around each other and separated by just over 1 light-year. Here, the binary system appears to have a combined mass of about 400 million suns. Astronomers confirmed the existence of the binary black holes by detecting gravitational waves emitted by them using the LIGO telescope. By analyzing observations of NGC 7674 made by the Very Long Baseline Array, scientists found two distinct compact sources of radio emission at the center of the galaxy. These monster black holes orbit their common center of mass about once every 100,000 years. The most likely scenario for how these black holes ended up spiraling toward each other is the merger of two galaxies to form the current NGC 7674. The only other galaxy known to have two black holes at its heart is a giant galaxy called 0402 plus 379, whose two giant black holes are separated by about 24 light-years. In 1973, Stephen Hawking predicted that black holes can eventually evaporate entirely, and for the first time physicists have confirmed. Professor Hawking suggested black holes are not perfectly black, and they actually emit particles. According to Hawking, this radiation could in the long run suck sufficient energy far from black holes to cause them to vanish. Even though the hypothesis was once seen as impossible to prove, it is now broadly thought to be valid. The so-called Hawking radiation is extremely faint for our instruments to detect in space, but scientists have seen this radiation in a black hole analog utilizing sound waves and some of the coldest matter known to humans. Even though the vacuum of outer space is generally believed to be empty, quantum mechanics states that a vacuum is full of virtual particles that pop in and out of existence. However, near a black hole, the massive gravitational forces will pull the particles apart, absorbing one into the black hole and shooting the other off into space. The escaping particle becomes known as Hawking radiation. The absorbed particle has negative energy which reduces the black hole's energy and mass, so if a black hole swallows enough of these particles it will eventually evaporate. For the first time ever, astronomers say they have detected ripples in space coming from a black hole eating a neutron star. On Wednesday the 14th of August 2019, the advanced LIGO detector in the US and the Virgo detector in Italy detected ripples in spacetime coming from a cataclysmic event about 900 million light-years away from Earth. Gravitational waves are created right before two massive objects collide. Astronomers analyze the gravitational wave data to estimate the exact size of the two objects and then figure out what each one was. If both objects are between 1 and 3 solar masses, they are most likely neutron stars. If both are more than 5 solar masses, the event probably involved two black holes. But on Wednesday's detection, astronomers found one object was over 5 solar masses, while the other came in under 3. That strongly suggests this is a collision between a black hole and a neutron star. Black holes and neutron stars are the super-dense remains of dead stars. However, scientists need some time before publishing the final results. Usually when we think about black holes, we think about destruction. But a new research suggests the radiation coming from a black hole could in fact help cook life on some music planets. Every star has a region around them where temperatures are just right for liquid water to exist on a planet. That region is called the G-low zone. A new study suggests that even black holes have a similar region. The swirling disk of gas and dust around a supermassive black hole is called the active galactic nucleus. This disk forms when a black hole eats matter from its galaxy. As the matter swirls, it emits extreme amounts of radiation and light. Previously, scientists thought this radiation could strip the atmospheres of any nearby planets, therefore creating a dead zone around the black music hole. Recently, researchers created some computer models of an active galactic nucleus to look at the swirling disk of gas and dust. Using these models, they detected galactic G deluxe zones surrounding black holes. Simulations show that if a planet is positioned at the right distance from the black hole, its atmosphere would remain intact, while the black hole's radiation could break the atmosphere's molecules into life-supporting compounds. This radiation could even power photosynthesis, a process by which most plants utilize the sun's energy to create sugars. This would be particularly important for plants on rogue planets, which are free-floating planets with no parent star, to provide a light source for a black hole the size of Sagittarius. The Galax region would extend about 140 light-years from the center of the black hole. Contrary to previous estimations, scientists now think the daging effects of black hole radiation would end at around 100 light away from a Sagittarius-sized black music hole. Astronomers using ESO's Very Large Telescope have discovered gas halos around some of the universe's earliest galaxies, formed more than 12.5 billion years ago. Those reservoirs of cooled gas provide food for the supermassive black holes located at the center of most galaxies. Black holes consume dust and gas from surrounding galaxies in order to grow. This explains how supermassive black holes, which likely formed due to the collapse of the first stars, were able to grow so large and so quickly in the early universe. Up until now, astronomers had not witnessed any evidence of enough black hole food to support the growth. Using the Very Large Telescope, the astronomers studied 31 quasars which appear today as they would have been over 12.5 billion years ago, when the universe was around 870 million years old, an infant in astronomical terms. 12 of those quasars were surrounded by huge halos of cool, dense hydrogen gas, extending 100,000 light-years from the central supermassive black holes. However, they remained closely bound, offering a potential food source for these supermassive black holes. The astronomer said that with the current studies, we are only just beginning to investigate how the first supermassive black holes were able to develop so rapidly. Astronomers from the University of California have found that powerful winds produced by supermassive black holes in the centers of dwarf galaxies can slow down or even stop star formation, impacting the growth of these galaxies. The winds were stronger than anticipated, showing black holes influence both large and dwarf galaxy development. Dwarf galaxies contain anywhere from a few thousand to a few billion stars. The researchers used data from the Sloan Digital Sky Survey, which maps more than 35% of the sky, to identify 50 dwarf galaxies. 29 showed signs of containing black holes in their centers, and 6 of those showed evidence of high-velocity ionized gas winds. Astronomers then used the CAC telescopes based in Hawaii to detect and measure the properties of these winds, marking the first time this has been achieved. Since larger galaxies often form when dwarf galaxies merge, studying dwarfs helps us better understand galaxy evolution in general. The cause of the winds is the material being fed into the black hole. As gas and dust fall in, friction and gravity heat the material and release radiative energy. That energy pushes gas out of the galaxy's center into intergalactic space. When the central gas is expelled, the galaxy's star-forming fuel is depleted and star formation decreases. The theory, which builds on ideas mulled over for decades, states that when something is sucked into a black hole, it is not lost to the universe forever. Instead, Professor Stephen Hawking says the information is stored not in the interior of the black hole, but on its boundary, the event horizon. What happens in the event horizon is rather complex, and even physicists struggle to describe it. One analogy based on a theory devised by Leonard Susskind and Gerard 't Hooft is that as a body falls into a black hole, its information leaves behind a kind of two-dimensional holographic imprint on the event horizon, a sort of bubble that contains the black hole through which everything must pass. Though you may be lost inside the black hole, the essence of you, the information about you, will stay smeared on the event horizon just outside. Hawking's theory is that the information can then escape again. He found that black holes aren't perfectly black. They give off energy called Hawking radiation, created very near the event horizon by small energy fluctuations in space. So Hawking now theorizes that this outgoing energy can pick up the information blueprint sitting on the event horizon and carry it back into the universe. Though the information might have escaped the black hole, it's not exactly its former self. The information has now returned in a chaotic and useless form. Many people have asked if the sun will ever become a black hole. The answer is no. It is true that stellar black holes formed by the gravitational collapse of a star, a massive star, but our sun would need to be about 20 times more massive in order to go supernova at the end of its lifetime and then collapse back into a black hole. However, there are also stars that are big enough to go supernova but still too small to become black holes. When these types of stars go supernova, they collapse into superdense structures called neutron stars. But what about the sun? In about 5 billion years from now, the sun will start to run out of fuel and begin to collapse. The sun's temperature will increase and its outer layers will expand so far out into space that they will engulf Earth. This time of our star is called the red giant phase and will last about 1 billion years before the sun eventually collapses into a white dwarf. A white dwarf is a small, very dense, burned-out core of a star typically the size of a planet. The outer layers of the sun's atmosphere which have been blown away will create a planet nebula that will glow for the next 20,000 to 50,000 years, expanding outward and fading slowly with time. Quasars are the brightest objects in the universe. They are powered by supermassive black holes and emit exceptionally large amounts of radiation. TON 618 is a very distant and extremely luminous quasar, an accretion disk of intensely hot gas swirling around the most massive black hole.